In Lesson 9.6, you're going to be solving systems of equations by graphing. And you have one vocabulary word, which is systems of equations. And systems of equations is just a collection of two or more equations with the same set of variables. So we have y equals 5x and y equals 30 plus 2x. Each of those has an x and a y. So that is called a system. And there's going to be multiple ways to solve a system of equations, and the method that we're going to explore in this video is solving by graphing. So you're going to want to have some graph paper. You can print off a couple sheets from the Google Classroom where I posted it, or you can ask your teacher for some. But when you're solving by graphing, our method of just making a really makeshift graph with the tick marks is not going to help us find the exact point where two lines cross. So keep that in mind as you're doing these problems. Of course, your worksheet has all of the graphs on them for you to graph. So in example 1, it says to solve the system of equations by graphing. So you're going to make both equations graphed on the same coordinate plane, and then you're going to find that point where they cross. So for example 1 here at the bottom, we're going to graph y equals x plus 2 and y equals negative 2x minus 4. So I'm going to pull this graph paper up here and graph the first equation, which is y equals x plus 2. I'm going to use the slope-intercept form, so I'm going to start by graphing my y-intercept at 2, and then I'm going to go up 1 over 1 because my slope is 1. Up 1 over 1. I can also go down 1 and to the left 1. And so those points fall on this line. And our second line is y equals negative 2x minus 4. So I'm going to go down here to negative 4, 1, 2, 3, 4, and put a dot. And then I'm going to go down 2 to the right 1. That's really not going to help me too much because I want to see where it crosses this other line. So I'm going to actually go up 2 and to the left 1, up 2 and to the left 1. And I know it doesn't look like that original line crossed at that point, but it does. So maybe you want to include a ruler or a straight edge when you're doing these problems because you are trying to find the exact location where those two lines cross. In this case, it's negative 2, 0. So let me write that ordered pair down and just check my solution, negative 2, 0. And this is my y value, this is my x value. So if I substitute those back into the original equation, does 0 equal negative 2 plus 2? Yes, it does. And does 0 equal negative 2 times negative 2 minus 4? 4 minus 4 is 0, so that checks out as well. So we would say that negative 2, 0 is the solution to this system of equations. For example 2, at the top of page 421, we have a story problem that asks us to write a system of equations. You cannot write a system of equations if you don't know what your x and y are going to equal. So that is always how you need to start. So y is going to be Marjorie's sales, x is going to be Brian. So Marjorie, y, is equal to 3 times x because she sold 3 times as many. And then also Marjorie is equal to Brian plus 12 because Brian sold 12 fewer than Marjorie. You're going to graph that system of equations on a piece of graph paper to find the exact point where they cross. And in this case, you can see that they cross at the point 6, 18. That ordered pair 6, 18 means that Marjorie sold 18 subscriptions because she is Y, and that Brian sold 6 subscriptions because he is X. For the example problem here, we have a similar situation where we have a story problem and we have to write a system. We have to start by saying what our X is going to be and what our Y is going to be. X is going to be our existing patients and Y will be our new patients. Now, if you chose the other way around, you should still get the same answer. It's just going to look a little bit different for your equations. But here we have y, your new patients, is equal to twice your existing, and then your new patients y is equal to your existing plus 22, and we got that from the story problem. Okay, now I don't have a piece of graph paper to go ahead and work this one out, so I'd like for you to try another strategy, which is not covered in this section, but you will also see it in a later section in our book. But when we have y is equal to 2x and y is equal to x plus 22, another way to solve a system is by substitution. If y equals this and y equals this, then we should be able to say that 2x is equal to x plus 22 because they're both equal to y, so we can set them equal to each other. And if I subtract x from both sides, I get that x is equal to 22. And if x is equal to 22, I can plug that value back in for x in either one of the equations, and I get that y is equal to 44. So without graphing, I solved this system by a strategy called substitution, and I got that 22, 44 is the ordered pair or solution to the system. So this is my x value, this is my y value. So if I translate that to what I said my x and y were in the beginning, I know that 22 is my existing patient number and 44 is my new patient number. If you want to go ahead and graph that, you can, but in this case, the strategy of substitution worked just fine. Okay, in example 3, we are solving the system again by graphing. Notice that step number 1 has you write them in y equals mx plus b form. You don't have to do that because you know that using a t-table is another strategy that you can use. But in this case, it's shown for you there, so I will model that at the bottom of page 421. The first one, y equals 3x minus 3, is already in slope intercept. And if I take x plus 2y equals 8 and translate that to slope intercept, I'm going to subtract x from both sides and get 2y equals negative x plus 8. Divide by 2, divide by 2. Y equals negative 1/2 x plus 4. So I have my two equations right here, and I'm going to go ahead and graph that on a piece of graph paper. To graph this on a coordinate plane, y equals 3x minus 3, I'm going to start by going down 3 on the y-axis and putting a dot there. The slope is 3, and so I'm going to go up 3 over 1 to put my next point there. So up 3 over 1, put a dot, up 3 over 1, put a dot. I could also go down 3 and to the left 1 to put a dot. And so that's my line right there. And again, if you have a straight edge, that's going to really be helpful because otherwise you can't find that exact position where they cross. And for y equals negative 1/2 x plus 4, I'm going to start by coming up to 4 on the y-axis. And since I want to see where they cross, I'm going to go down 1 to the right 2, and that's where I see where they're going to cross, which is that point right there, which is over 2, up 3. So 2, 3 is my solution. 2, 3 is where the two lines cross. That's also referred to as the solution to the system of equations. On example 4, it says to graph each system of equations by graphing. Notice on letter A, we have two lines that are parallel, meaning that there's going to be no solution to this system of equations. We also have a situation in B where the two lines are the exact same line and they're graphed right on top of each other, so there's infinitely many solutions. So make sure that you get this little chapter summary on your notes, because just like equations, we talked about most of the time there is going to be just one solution. That's right here where they cross. Same thing with systems of equations. However, sometimes we get an equation where there's no solution, and in this case, when you're graphing, it's two lines that never cross. They're parallel, so there's never going to be a time where there's a solution. And then on the third example here, we have infinitely many solutions because it's the same line. So for 4a, y equals x plus 4 and y equals x. If you graph those, there's no solution. I'm going to give you a little hint here. When the slope is the same, in this case the slope is the same, you're going to have parallel lines and there's going to be no solution. Okay, in this case, y equals 1/2 x minus 1. If we wrote this in slope-intercept form and took away x from both sides, we would get negative 2y equals negative x plus 2. And when you divide by negative 2, you get y equals a positive 1/2 x minus 1, which is the same line as the first one. So we're going to have infinitely many solutions. Key concept here on this chart, and we will go over it when we meet together in person, but just make sure that if you need any extra help, you check out the video tutors, and also Khan Academy will probably have lots of different videos for you if you type in solve by graphing. And then of course you can always request a Google Hangout with me if you need some extra help. In Lesson 9.7, we're going to be looking at solving systems of equations algebraically. In Lesson 9.6, we talked about solving systems by graphing, but as with any topic or concept in math, there's always more than one strategy that you can use. And graphing does have its benefits because you can visually see where those two lines cross, but sometimes, as I mentioned in the previous lesson, graphing is not always the best strategy because you might not have graph paper available, and or the y-intercept is too high of a number for you to start graphing. So you need to have another strategy available, which is called substitution in this lesson. And this method is going to do exactly what the name suggests, which is substitute in one of the equations into the other so that you can solve for one variable. If y is equal to x plus 2 and y is equal to 5, then we should be able to put 5 in anywhere we see the letter y, the variable y. So we're going to put 5 equals x plus 2, and if we subtract 2 from both sides, we get x equals 3. So this is graphically how that looks. The ordered pair 3, 5 is the solution, 3, 5. It's where those two lines cross. So we are going to do this at the bottom of page 425. If y is equal to 5, then we should be able to put in 5 wherever we see y. So we have 5 equals x plus 4, subtract 4, subtract 4, 1 is equal to x, which is what we see right there. And if 1 is x, and we plug that back in, substitute it back in, 1 plus 4 is 5. So the solution to that system of equations is 1, 5. For 1b, we have x is equal to 3, so I should be able to put that in wherever I see an x and then evaluate. So y is equal to 7 minus 3. 7 minus 3 is 4. That's my y value. And then if y is equal to 4, then we should be able to put that into our equation, and our first equation, and we have 4 equals 7 minus x, subtract 7, subtract 7, negative 3 equals negative x, so positive 3 is equal to a positive x. So the ordered pair 3, 4 is the solution to that system of equations in 1b. Finally, in letter C, 1c, x equals this and x equals this, so we should be able to put in that negative 3 wherever we see an x. Negative 3 equals y plus 4, subtract 4, subtract 4, y is going to be equal to negative 7. And right here it says x equals negative 3, so that's it. We would also get the same answer if we put negative 7 in for y in the first equation. Negative 7 plus 4 is negative 3. Okay, so sometimes one or both of the equations in a system are written in standard form. We've learned about slope-intercept form, which is y equals mx plus b, but standard form is written ax plus by equals c. In this example 2, you'll notice that the two equations are not written in slope-intercept form, and they're not written with a single variable like we saw before. In the previous example, we saw y equals 3 and y equals x plus 7. We had an isolated variable. But in these equations, notice that we have x and y on the same side, and what we're going to try to do is isolate one of the variables. In this case, this single y stands out to me, and I can get rid of the negative 3x by adding it to both sides, so that I get y equals 3x minus 13. And once I know what y equals, I can substitute in that for the second equations and then evaluate. So example 2 is going to get a little bit trickier, but go ahead and make sure and look through the example and get all of these steps down for 2a and 2b. I'm going to start with 2a, and what I'm looking for is a single variable like this y. So I'm going to take away 4x, to get 1 minus 4x equals y. Because it equals y, I should be able to take whatever y equals and put that in for y in the first equation. So this is how it looks. 2x minus 3y, y is 1 minus 4x, and then that equals negative 10. I need to distribute the negative 3, so I get 2x minus 3 plus 12x equals negative 10. 2x plus 12x is 14x, and then add 3, negative 10 plus 3 is negative 7. Divide by 14, x equals negative 1/2. So if x is negative 1/2, I can put that in for x here. Let me go ahead and erase that. If I put negative 1/2 in for x, negative 1/2 times 4 is negative 2. 1 equals negative 2 plus y, plus 2 plus 2, y is equal to 3. Okay? Again, it's a little bit trickier, so you're going to have to pay attention on these ones if it's asking you to solve algebraically. In 2b, I do not see a variable by itself without a coefficient. So what I need to do is pick an equation, it doesn't matter which one, and isolate one of the variables. So in 2x minus 4y equals 6, I'm going to add 4y to both sides and get 2x equals 4y plus 6. And then divide by 2, and get x is equal to 2y plus 3. Wherever I see an x now, I should be able to plug that into my equation and get my answer. So 3x, or 3 times 2y plus 3, minus 5y equals 3. All I did in that step was put what x equals in for x in my second equation. Now I'm going to distribute and get 6y plus 9 equals, minus 5y equals 3. If I subtract 9 from both sides and combine 6y minus 5y, I get y is equal to negative 6. Once I know y is negative 6, I can plug it in anywhere I see a y and solve for x. 2 times negative 6 is negative 12. Negative 12 plus 3 is negative 9. So the solution to that system of equations is negative 9, negative 6. And if you were to graph those two on graph paper, you would see that they cross at that exact ordered pair. For example 3, you're also solving a system of equations algebraically. Again, you're looking for a singleton variable and what that equals, because then you can plug in whatever that equals into the other equation for that variable. And so in 3a, we have y equals negative 2x plus 4. So wherever we see a y in that first equation, we should be able to put in parentheses negative 2x plus 4. And then we utilize our distributive property to get 4x minus 4x plus 8 equals 8. And then we get 4x minus 4x, which is 0. And when you take away 8 from both sides, we get 0 equals 0. There are infinitely many solutions to that system of equations because it's the exact same line graphed on top of each other. So those are the same exact lines. In example 3, we have x minus y equals negative 4. And I'm just going to solve that for x by adding y to both sides. Plus y plus y. X equals y minus 4. And so let's put y minus 4 in for x here. Y minus 4 minus y equals 1. We have y, take away y, which is 0, and then we have negative 4 equals 1, which we know is not true. So there is no solution to that system of equations. At the top of page 427, it says that you can use system of equations to represent real-world situations. And so in example 4, we have a story problem that we can use to write a system of equations. So make sure you look through the examples here. I know that I'm only going over the parts that you need to write in your notebook, but looking at the examples helps. Also checking out the video tutors gives you one more example if you don't understand how to do any particular example. I'm going to go down here to the got it problem. It says the length of a rectangular garden is 4 times its width. So I'm going to utilize another strategy I like, which is to draw a picture. It says the length is 4 times the width. So here's the length. Here's the width. So the length is equal to 4w. Okay. The garden has a perimeter of 280 feet. Well, the perimeter is 2 L's and 2 W's. So that's 2L plus 2W equals 280. And there we have a system of equations because we have two equations with the same variables. Okay, so it says write and solve a system. So here's your first part of that. L equals 4W and 2L plus 2W equals 280. Notice that they used X and Y. It doesn't matter. Okay, and because L is equal to 4W, I should be able to put in 4W wherever I see an L in the second equation. So that looks like this: 2 parentheses 4W plus 2W equals 280. This is 8W plus 2W equals 280. 10W equals 280. Divide by 10, divide by 10, W equals 28. So the width is 28 feet, and if the width is 28, I can plug in 28 to this equation or this equation, it doesn't matter, but plug that in to find out the length. 4 times 28 is 112. Okay. Again, this section gives another strategy for solving systems of equations. It's probably my favorite strategy algebraically. I do like to graph it, but sometimes that takes too much time and I need to make sure that my graph paper is big enough to handle the numbers. But algebraic is really slick and it gives you the answer using algebra. There are a couple other strategies that we'll explore when we meet face-to-face, but for now, just make sure that you utilize your tools and resources to make sure you understand this strategy, and let me know if I need to do a Google Hangout or provide you with more resources. Thanks.